Okay, the talk is now being recorded. So thanks everyone for making it on time. This will be the new normal time, 6 p.m. UTC. There are a couple time changes all over the world, so this may or may not move for you again by an hour in one of the directions. I don't actually know which way daytime saving goes. So this week we've got Yuda Song from CMU, and we've got Chi hosting him. Please, Yuda, go ahead.
Thank you, David. It's my great pleasure to be here. And today I'm gonna talk about our work on hybrid RL. And this is joint work with Ife, Ayush, Drew, Akshay, and Wen. And as the title of the talk suggests, we're going to talk about this RL paradigm where you can use both offline and online data. And this is, as we're gonna show, gonna be an efficient RL paradigm. And for the outline of the talk, for the first part, I'm gonna give some motivation on what are the advantages of this setting. And for the second part of the talk, I'm gonna introduce a specific algorithm under this hybrid RL setting. And I'm gonna show you some result from the algorithm. Also, I just wanna mention that it has been 1 year since we put the paper on arXiv. So there has been a lot of great new works in this field. And I will very briefly touch upon them at the end of the talk. Feel free to let me know if I missed anything, and I'm happy to discuss at the end of the talk or after the talk. And personally, I am very excited about this setting, and I think there are a lot of interesting questions to solve. And I hope at the end of the talk, I can at least convince you this is a very nice setting to study. And finally, I just want to mention that since this hybrid RL setting is kind of like an interaction of fields or settings, I'm going to make a few comparisons according to my best knowledge. So also, please feel free to jump in and let me know if I missed anything during the comparison. Okay. Now let's jump right in. We can start with the following question. Can we design provably efficient algorithm for rich function approximation and model-free RL? Okay, so why specifically these two settings? For the first part, as the RL theory community evolves, we are having better and better understanding on the canonical problems. But real-world applications are generally large-scale and require rich function approximation, say, neural networks. And for the second part, in real world, model-free algorithms are actually more convenient, more popular, and has more successes in applications, at least to my knowledge upon until this point. So now I hope this question sounds important and interesting to you. And let's see how we can solve it.
Could I ask a quick question about this?
Yeah.
So when you post a question like this, are you kind of like implying the rich function approximation plus model-based setting is like already solved, or you're not interested?
I think like at least to my personal taste, it's like rich function approximation plus model-based is like less interesting to me because
so you are just saying you're interested in solving those
yes,
two
yes.
Okay.
Yes. We will actually see some examples, at least in the hybrid RL setting, in the model-based setting. But like there are some nuances. Maybe hopefully I can cover them through the talk.
Okay, I also have a quick question. So both the rich function approximation and model free, are they both dealing with large state and action space?
Yes, that's what we mean by like rich function approximation.
Okay.
Yeah.
Okay, thank you.
Yeah, thank you for the question. Okay, let's try answer this question, and let's attempt it with maybe the most obvious answer. So let's just try to run some popular online algorithm, say PPO, which we know have a lot of successes in the real world already. But as we also know, online RL with this naive exploration, for example, like if you do random exploration, say you run PPO with the entropy regularization, or you use some heuristic exploration without knowing the structure of the problem, will incur a large amount of sample during training. Okay, in some settings, this is okay. Say if you play video games or if you use a simulator, but in others, they're not, like if you train a real robot or like doing clinical trials. Since every samples or every interaction you have in the real world has some cost, so you do want to learn with as few samples as possible. So in fact, let's see a learning curve of online RL algorithm with heuristic exploration on a standard Atari benchmark. And you see online RL indeed use way more samples than necessary. And we will demonstrate that actually very few samples is enough if you're learning with the right strategy. So let's try keep trying to.
So you just want to make clear this HighQ is your algorithm in the graph, and this R&D is the classical algorithm.
Yes, it's a very classical baseline for this, like Montezuma benchmark. And yes, HighQ will be the algorithm that we're gonna introduce. So this is kind of like a spoiler for the talk. Yes, it's our algorithm that we are gonna talk about today. But we'll see it again. Yeah. Okay, here's the outline. We just mentioned that if we do not do, say, structured or informed exploration, we do need a lot of sample. So what if in some nice situation, we already have a lot of data at hand? So can we leverage them so we don't have to collect a lot of data online? And the answer is yes. Having a lot of data at hand is indeed possible. And we do have big data set on decision-making problems out there. On the left is the Eagle40 data set, which is videos of like human interactions, playing sports, and various 3D scans. And on the right is the very recent RTX robotics data set with like multi-modality inputs, actions, rewards for different tasks like picking, pushing, folding, and many other different ones. And also like you have like internet level data set like YouTube videos. So it's great that we have very large size of data set, but apparently they have mixed quality. Say like the robotics data set you collect can be collected with different level of expertise, or not even saying like say if you want to learn how to play Minecraft, you watch YouTube videos. Sometimes they are good, sometimes they are bad. So like the lesson here is you cannot just run imitation learning on this mixed quality data set. But gladly we have offline RL. So like in offline RL, we train a policy on this mixed quality offline data set, but in a complete offline manner where we don't interact with environment at all. So there, again, as we all know, there are some challenges for offline RL. And the first one is the pretty well-known distribution shift problem. So even though we have this large data set, but for some specific tasks that you care about, we still do not hope that our data set covers the whole state action space. So from the algorithm side, people usually just utilize pessimism. And we know that if you want some general level algorithm for offline RL, implementing pessimism are challenging. And so far, I think we only know like algorithms with very computationally heavy articles. And the second issue is to do complete offline RL, like the elephant in the room is we actually need to verify the performance online. And here it is 2 online performance curves of 2 deep offline RL baselines. And we can see their offline performance actually fluctuates a lot. But if you only look at your offline objective, the curve may already converge very nicely. So in order to get the best policy or to do hyperparameter tuning, I think so far the best strategy is still just roll out your policy online. Any question on this part?
Yuda, just also another quick clarification question. You mentioned you run 2 offline algorithms and they fluctuate a lot. You're saying this is bad or this is not bad? Or?
Oh, this is actually like not great, because if you only look at, without this online interaction part, right? So you actually cannot decide which final policy you want to return, right? Because like the curve, if you look at like post hoc online, from one iteration, it could be have like a return of 80s, and then next, after one update, it goes down to like 40 or 20. So if you do
this is across the training. So this time slice is like across the offline training. Sometimes
right.
goes very high, goes very low. Okay.
Right. Yeah. And also like these are not plots that I made myself. They're from like some, the citation is under the slide. So it's like someone did that in their paper, and I just copied the.
And also Ziyi from the audience also has a question. She asked like, can we reduce the fluctuation simply by smaller step size or larger batch sizes?
I think it could be possible. I think like this part is a very interesting question to like pursue future like researches. Like, how do we actually say if you want to address it in a complete offline manner, how do we do that? There is some like I think there is some like theory research on that already, but like I think they still need extra assumptions to deal with that. But like I don't have a good answer so far. Yeah. But like the point is still like at least at this point is doing it in the complete offline manner is, at least to me, seems still pretty challenging. And yes, like if you do offline RL, there's this at least 2 known issues. Like one is the computation issue if you want to do general pessimism, and the other one is like you need some online verification. And okay, then we still have another route to go. So what if we assume structures and we can perform informed exploration? So let's leverage the structure of the problem. And again, I think everyone is familiar with this diagram, but let's just quickly recap. These are the known statistical tractable problem. However, we only have like a efficient algorithm, Oracle efficient algorithm up to like the low rank MDP setting, at least at this point. And there is this recent result from Daniel, Sihan, Shahar, Gaurav, Chaba, and Gellert that show some exponential hardness in computation in the low bilinear rank model. Specifically, I think they showed like a Q star and V star model. And then I think this is saying like maybe designing optimism in general function approximation is like probably challenging. And it seems like there is a real statistical computation trade-off, at least in the current general models. So again, if we only leverage a structure, we have the statistical benefit, but we still face the computation problem. And how do we overcome these challenges? So let's look at our toolkits.
And also another question. The structure you kind of talk about are all online algorithms, right?
Right.
Also following the online bucket or something.
Yes,
like
yes, it's following the online literature. Yeah. But yeah, thank you for the clarification question. And but let's look at our toolkits, 3 toolkits here, and maybe like if we combine some of them together, we can obtain some benefit. Say one obvious thing maybe to start is to combine online and offline RL. And like from a very intuitive level, and we'll show later, and if you combine both online and offline, and if your offline data is somewhat good, then maybe you don't need to do pessimism or optimism, which I believe is the source of the computation difficulty from the previous data return. And formally, this is the offline plus online setup. And I'm gonna use the word offline plus online and hybrid RL interchangeably through the talk. And we start with some offline data, and we also have this online interaction access. And during online, we will aggregate more online data. And during training, we will combine both online and offline data with whatever algorithm you want to use. And there are already a lot of work in this setting. In the application side, for games, you have the first AlphaGo actually use both like offline expert data, and during online, you have this self-play. And for robotics, there's already a lot of applications using demonstrations to speed up the online learning process. And of course, I would also put like ChatGPT into this category, where you first pre-train your large language model using expert human language sentences. And during the online stage, you do RLHF. And there also works on the theory side. And if you have a reset model, you can do like CPI or PSDP. And this is the model-based part that I was hinting before. So like already there is model-based RL works in this hybrid RL setting. But I think like the proof technique they used is like using some like no regret guarantee instead of using known structures. So that's like, I don't have like a great category on how to categorize this. So, but yeah, like they are already like, I'm saying like there are already like previous model-based works in this setting. And also like Tengyang and Nan has this nice paper in this offline plus online setting in the tabular case, and which they also provide a lower bound. And okay, so we see like for the hybrid RL setting, indeed you can have like achieve efficiency if you have say reset, or if you do model based, and if you have demonstrations instead of mixed quality offline data. But that's not the answer for our question that we posed at the beginning of the talk. So, but we still have our third toolkit. So in this talk, I'm going to show
Yuda, there's a question in the audience regarding the drastic data distribution shift. Do we know what is the tolerable limits within which the performance can be guaranteed? To what extent and how does combining both offline and online help in such cases?
Oh, that's a great question. Like, I guess, like in the offline RL literature, people always use the characterization of like coverage, right? Say, if your offline data set does not cover any good policy at all, if you think of offline RL, like it only covers the bad regions, then I don't think there's any hope you can do it in offline RL setting. And I will give a more confined definition of like similar, like what is how much we can handle this like out of distribution issue further later in the talk. But like on an intuitive level, it's basically the same level as like how offline RL can handle like this coverage or distribution shift.
Yeah, I think basically provide you're saying like more technically is like we have this concentrability essentially says measures the distribution shift between the data offline data we have and also the policy we're trying to cover. And so previous work offline work already have these measures, and you have sharper one, you have looser one. I think this work achieved the sharper one, right?
Yes,
but does not improve upon that.
No, it's not like we introduced any like brand new notion of coverage or like out of distribution shift manner. It's just slightly sharper.
Thank you.
Thank you for the question. But yeah, as I was hinting before, in this talk, I'm gonna show in the offline RL setting, if you incorporate structure, you indeed can have a positive answer to the questions that we were posing before, that you will have efficient model-free RL algorithm with rich function approximation. Okay, before we dive into the technical detail, I actually have one more motivation for why people should care about this hybrid RL setting. But I think we're slightly left behind. So I'm gonna quickly skip this slide, but we can go over this like if we have more time at the end of the talk. So here's the technical part. So this is the setting. And we start with the online part of the setup. And we care about episodic finite horizon MDPs. And unlike like some previous work like CPI or PSDP, we assume that we can only reset from the initial state distribution. And the offline part of the setting is we have this offline data set that is sampled from some offline distribution. And we have state action reward and next state tuple. And we assume that, as the question was asking before, like we assume that offline data set distribution covers some good or high quality policy traces. So I'm not giving any definition about what this actually means for now, but we will see later. At this point, I think you can just think of it as like density ratio or whatever your favorite coverage term is. And we're gonna deal with function approximation, specifically like Q function approximation. And we're gonna assume realizability. That is like the optimal Q value and Q functions is contained in our function class. And our learning goal is we're gonna try to find a policy that is at least as good as the best one covered by the offline data set. I know like this is slightly unusual with the like the usual learning goal that to find the globally optimal policy. But let me just give you a quick intuition why this makes sense. Imagine like you're doing this hybrid RL setting, and if I gave you completely random data for the offline setting, and I also promised you that I won't do any explicit exploration online. So you can imagine like the offline data actually do not help you. And the best, I don't think, at least in this case, you can say, hey, I will actually find the globally optimal policy if I don't do active exploration. And this is at least my intuition on how do we justify this learning goal. But I think this will, as we'll see later, this is actually like a pretty good guarantee already. And at the later of the talk, I will also show you that we can actually slightly relax this learning goal to a more general one. Any question about the setup? Cool. So now we're
just a second. There's another question from the audience from Ethan Lee. And he asked how to compare with the generative adversarial imitation learning with moment matching. Or Ethan, do you want to jump out to say more about what is like generative adversarial imitation learning with moment matching?
Sorry, yeah, I gotta say explicitly, it's like we also have the offline expert demonstration. We are in online interaction. We match the state action occupancy measure to match our online interaction state action distribution to the offline expert demonstration, so that we're gonna finally achieve also similarly the comparable performance with the offline demonstration expert.
Oh, does the offline data only contain expert demonstration? What's the quality of the offline data?
I think in the ideal case, it's just the expert demonstration. So we don't assume those like 50% mixing or all those. Or there exists some work that randomly makes random action with expert and do similar stuff. But yeah, I think ideally it's just the expert.
Yeah, I think like the problem is like the problem setup is definitely more ideal if your offline data only contains the expert, and you can do various things like imitation learning or the thing you just mentioned. I think it will work great. And I think in our setting, it's more like you don't actually know the quality of your offline data, and the coverage, as I show later, is like it doesn't have to be like your offline data has to be collected by expert policy itself. It's the coverage term is like more implicit or nuanced definition of coverage.
Yeah, I think yeah, that explains.
All right, thank you for the question.
Yeah, thanks.
Okay, cool. For the algorithm, it's actually pretty easy. We call it hybrid Q iteration. We call it HighQ. And in high level, HighQ is just you run FQI fitted Q iteration on the combination of offline and online data. And here it is. For each iteration, when you are running your algorithm, and you first gonna collect more online samples with your current policy PyT, and then you're gonna aggregate your online data set from all previous iterations. And finally, you're gonna run fitted Q iteration on the combined online data aggregation plus your offline data set. And that's it. And fitted Q iteration will return you a new policy, and you will use this new policy for your current policy in the next iteration. Okay, I'm sure many people here are already familiar with what fitted Q iteration is, but let's just quickly overview it. Fitted Q iteration is this dynamical programming style algorithm that just doing regression on the whatever data set I gave you. So basically, if you look at iteration 1 and 2, it's saying we're gonna do regression from the last time step or last horizon all the way to the first horizon. And in each time step, basically you're just doing least square regression to minimize your Bellman error. And that's it. And at the end of the day, your policy is just gonna be the greedy policy with respect to the function or Q functions that you learned. And as you can see, this is a pretty clean algorithm, and all you need to do is just keep doing regressions on the combined offline and online data set. Okay, and that's the algorithm part. And now we're gonna quickly go over the theory result. And the assumption we make are first, we're gonna assume the Bellman completeness, or you can have some like small misspecifications. That's okay. But like for cleanness, let's just assume you have Bellman completeness, where it's like for every function in your function class, its Bellman backup is also contained in the function class. And the second assumption we make is like basically the structure assumption. Like we are assume like the MDP that we are in plus our function class has this low bilinear rank structure. Okay, well, for people who are not familiar with this, what does this mean? So it's saying for any two functions, f and g, in your function class, the absolute expected Bellman error of function 1 f under the distribution induced by the function 2 g has this bilinear structure, which each term in the bilinear structure in the inner product is defined by the function g and function f respectively. Okay, some visualization. Imagine this like huge matrix where each row of the matrix is defined by each function in your function class, and each column of the matrix is also defined by your function class. And then each element in this matrix is basically just this like expected absolute of the expectation of the Bellman error of function 1 under policy 2. And we say you have low bilinear rank, say bilinear rank D, if this huge matrix only has rank D. Okay, I hope this makes sense.
I think in short, the intuitive explanation is like you have two things you want to decouple. One thing is you have a rolling distribution that depends on one function, that is g. The other thing is the error will be measured on this function f. And this is saying the Bellman error, which depends on these two things, can be linear decoupled into like inner product of two things with some inner product in the d-dimensional space.
Yes, yes. Yeah, thank you.
Are there like any application or like any examples to motivate this assumption, or is this assumption also used before in previous literature?
Oh yeah, this is like proposed in the bilinear classes paper. I think I don't remember the title. Yeah, I should have given a citation under here. But yeah, this is like, and also
I think you have the slides which you have like a lot of box, and this is like one of them, and it contains a lot of tabular, linear, a lot of examples.
Yeah. If you go back to check the slides on the online structure, the big diagram, it's like the second biggest one other than DEC. Yeah, that's the assumptions we make. And now I'm gonna introduce, as I promised, what do I mean by cover? So we use this coverage for this work. It looks very intimidating, but I promise you it's not. Let me quickly explain it. So the coverage is with respect to some policy pi that we care about, and thus we write it as C pi. And the term is basically the worst. If you look at every function in your function class, and what is the worst case function in your function class that you're gonna have, we call it max f over the f function class. And on the numerator, you have this average sign Bellman error of this function f under the policy pi that you care about. And on the denominator, it's just the average square Bellman error of this function f under the offline distribution. So basically, it's saying how well your offline distribution covers the Bellman error induced by your functions that you care about. So I hope this is intuitive, and this is actually pretty nice because it's smaller or sharper than the previous definition of coverage in the offline literature. So if you put it in the tabular case, it will be smaller than the density ratio. And if you put it in the linear case, it will be smaller than the relative condition number. But
when you say smaller means when you say put it in, it means you kind of like choose a particular function class. Like for tabular, you just choose any function, like the entire function class.
Yes.
And
Yes.
for linear, you choose a linear function class.
Yes. Yes.
And you say it's sharper, it's equal, or it's actually strictly less, or
strictly less, I think by Jensen or something.
And could you explain a little bit more, like in the tabular case, why it's strictly less?
Okay. If you
or maybe just intuitive, like in high level, yeah.
Okay, let me see.
Or from like what perspective it could be tightened, because like the right hand side seems like the density ratio seems like pretty tight in some sense.
Yeah, I think if you put the similar thing in tabular on the
So you're just saying it's something complicated, but you can prove by Jensen's inequality or something it's less equal to the right hand side.
Yeah.
Okay, that sounds good. Yeah, sure.
Yeah. Sorry, I cannot give a very good
no
intuitive. It's not like super intuitive, but yeah. And people complain because like this looks actually pretty ugly.
Chaba actually raised a hand. Chaba, go ahead, please.
Yeah. So I just want to clarify whether we actually know whether this constant can be strictly smaller than the right-hand sides with the appropriate matching of the function class, or we just know that the inequality definitely holds, and we don't know whether it's an equality.
Yeah, we proved it in our paper.
Okay, so there are some examples where there is a strict inequality.
No, we don't give like exact examples, but like where it's strict.
So maybe they're equal.
Yeah.
Who knows?
Yeah. Maybe I should say like no bigger than, or
yeah.
So what you're saying is you prove it's less or equal, but not necessarily strictly less. It's just less or equal.
Yeah, I think so. Yeah.
That sounds good.
Yeah.
And also Ziyi has another question. Ziyi, do you want to go ahead to ask it?
Oh yes. Actually, I found it strange that in a nominator, in numerator you use one norm, but the denominator uses the two norm. However, from the right side, it seems the both nominator and denominator, they seems to be symmetric. So
yes. Excellent question. Like many people complain about it, and I don't think we have time to go over what's really going on here, but I can refer you to this excellent thread from Nan, where he reflects what exactly is going on with this ugly coverage, and why it's not symmetric, and why it's like no bigger than or sharper than the previous ones. If you're interested, I highly recommend you check out his thread. Yeah.
Oh, if I may jump in, I think that it's interesting that there is not an absolute value in the numerator. So maybe that's going to lead to a strict inequality because there is no symmetry in terms of the changing signs of f is not going to give you the absolute value inside, right? So it's like, oh, okay. No, it can be strictly less because of that.
Yeah, I think like, okay, this is what happened during the paper writing. We started with absolute sign. And later when we write the proof, we realize, oh, actually you don't need the absolute sign on the numerator. But like you do have the, like it can be smaller than 0. That's why we put like max 0 and this thing. Yeah. Does that make sense? On the numerator.
That sounds good. We can go on.
Yeah, we can discuss more at the end of the talk if there's still confusion. Sorry if I'm not explaining this clearly enough.
No, that's very, very good already.
No,
thank you.
Yeah. Okay. That's the assumption part, and this is the main theory result. And we prove that for the HighQ algorithm with high probability, you can compare with any comparator policy pi e, which is covered by the offline dataset, with this regret bound. And let me just give a quick intuition about what's going on here. So if you cover the, if you cross out the coverage part, the max one coverage part, the remaining regret bound is basically the state of the art regret bound in the bilinear classes problem by the bilinear UCB algorithm, but it is not computationally efficient. And since we are dealing with offline data set, so I guess naturally we will also pay for the coverage part. So that's, I guess, intuitively to understand what's going on with this regret bound. And okay, let's say even in a nicer situation where the optimal policy is covered by the offline data set. And then we can compute to the optimal policy in polynomial number of samples. And more importantly, we only need a polynomial number of calls to the least square regression articles. This is I think is a clear improvement over the pure online algorithm where you don't have this, you have this computation infeasible algorithm if you do global optimism. And the story here is, if your offline data set covers high quality policy, then we can reduce this large family of RL settings by just solving least square regression problems. And here's a one-page proof sketch. I promise it's gonna be very fast. So with a pretty standard decomposition, we can decompose the regret term into these two Bellman errors, and note that the first term does not have absolute sign. So that's why in the coverage term, we don't have the absolute sign in the numerator. And the first part is basically the signed Bellman error of your current value function under the comparator policy. And this part is easy since you keep doing FQI over this fixed distribution. So if your offline data covers this comparator policy pi e, then this term should be small. And the second part is slightly trickier. It's the Bellman error of your current value function under current policy. And since, again, you are doing FQI, so the current value function should have small Bellman error under the mixture of all previous policies, not the current one. But one of the two things will happen. One is if your current policy's distribution already being covered by the previous policies, then you're already down. And otherwise, just think of you explored. And thanks to the low bilinear rank structure, you cannot explore too many times. So without having explicit exploration, we are already having this explore or terminate flavor in our analysis. So here is something that hopefully can help people better understand where the computation benefit is coming from. It's an analogy between the previously already existing model-based computation gain to our model-free setting. So now we are just gonna compare with offline RL literature. Online RL, when you do global optimism, it's basically the same when you do general setting offline RL with global pessimism. So I'm just gonna write one of them. And in the model-based setting on the upper left corner, in the general setting, you need to do this version space algorithm where you find the mean over all possible models that has small, say, MLE error. And on the right-hand side is like the previous work in the hybrid RL in model-based setting, where you can just do MLE on the combined of offline and online data set, and then you're good. Like all the computation oracle is just the MLE oracle. And we now, like in this work, we introduced this analog in the model-free setting. And in the model-free setting, in offline RL, if you want to do general case, you still need to do the version space algorithm, finding the most pessimistic value function with small Bellman error. But in the hybrid setting, you just need to find with least square regression, you can just find a policy that has small Bellman error on the combined of offline and online data set. Then you're pretty much done.
I just want to ask questions about this slide. So you're trying to say the previous offline algorithm are mostly minimax, or?
Yes, if you want to do general, say if you don't want to do like LCB, or like you already assume you know the structure or something, right?
Like the pessimism is not here, or pessimism is also minimax?
Like
for example,
pessimism,
the pessimism.
Oh, pessimism is already here, right? Like you have this mean over, or.
You can also view pessimism as a minimax algorithm.
Yeah.
Okay, so this is like in terms of comparison for the algorithm style.
Yeah. Like, oh, yeah, yeah, sorry, like one clarification is like, I'm not saying like generally like, we know any like fundamental barrier for preventing you to do like computation efficient algorithm in offline RL in the general setting. It's just like the current algorithms that we know are like have to do this like version space algorithm to ensure pessimism. Yeah.
Sounds good.
Yeah. Okay. I also promised you earlier, it's like our learning goal is like slightly non-normal, because we only compare with the best policy covered by the offline dataset. But can we do better? Okay, we have our offline dataset, and this is the best comparator policy. But let's also consider the possible distributions that we're going to cover during online. And with a slightly more careful analysis, we can show that you can compare with the best policy that is covered by the combination of the online and combination of offline and the online distributions that you covered. Okay, but this is still like, I have to admit, this is still slightly unorthodox, because like your online distribution depends on your algorithm, right? So, and also like this still does not guarantee you the global optimality. But
what you're saying is like you don't have a lot of control over the online policies. Like it's just algorithm will run the algorithm and then it goes through some policies, and you don't actually know much about the property of those policies.
Right.
Actually, Chaba has a question. So yeah, please go ahead.
Yeah, maybe related to this is that I'm thinking about cases when, I don't know, you have, let's say for simplicity, a tabular case, and you have two policies that you're using for collecting data. So it's basically a mixture policy that you use for collecting data. And then it's like this pasting together trajectories idea, that like one policy would generate trajectories up to this point, and then it would go this way. And the other one is like maybe coming this way, and then coming to the same point and generating data from there. So the two together kind of cover everything, but none of them alone covers everything. So that was included in the original definition, I suppose.
Yeah.
So in this case, if you have kind of like all the information is there, but they were not ever part of the same trajectories, then we would be assured that this offline plus online way of running FQI is going to discover the optimal policy in this setting, or a near optimal policy. Correct?
Yeah.
Yeah.
So it's stitching problem is covered.
Yeah.
Right. Yeah. I think this stitching is only like this part of the mu h plus dh is only like the rowing policy, but then you can do some stitching.
Yeah. So the statements are given for like what, like there is no condition on how the trajectories are generated. There can be, every trajectory can be generated by a different policy in your offline data.
Right.
Doesn't matter, right?
No. It doesn't have to be a like.
Okay. Because I think that this teaching is kind of what's interesting. In a way, you want to cover it for sure.
Yeah, but like
Good.
I don't know if like in the pure offline setting, if there's any separation, if like your offline data set is like pure trajectory versus you have more freedom.
There are some very slight differences sometimes, it seems.
Yeah. Thank you.
Or big differences, but like yeah, it's a bit technical.
Yeah. Thank you for the question. But like I just want to briefly mention that in some case, like in the worst case, it doesn't have any benefit. But like in some case, say if you're doing epsilon greedy is easy, or like incorporate a slight exploration online, and it will cover much more region, it will be beneficial. And I would recommend check out this great paper from Chris and Irish on the characterization on like how when epsilon greedy is easy. Okay, we are gonna run out of time, so I'm gonna quickly go over the experiment part. The baseline, the benchmark we run, as I told you before, is the Montezuma rerun, just one of the experiment we run, where you have image state and many actions and extremely sparse reward signal. And for the offline dataset, we mix half and half from expert policy and a random policy with like 0.1 million samples in total. And this is the training curve. Hello again. And we see like our HighQ algorithm quickly discovers the optimal policy, and using the same number of samples, like this like baseline, popular baseline R&D has barely started. The video gonna run a while, but I guess
So also another clarification is I just want to say the starting point seems also a bit different, right? For R&D is trained from the scratch, while your HighQ is actually starting from the offline part, right? You already did offline IO for your algorithm.
No, it's like we are also starting from scratch.
Oh, you just put the data set into your algorithm.
Yes.
Okay.
But like there are like a lot of other works that do like offline pre-training and then do. It's called like off to on setting, which is also very interesting.
Okay, so you can say that the policy is trained from scratch, but just at the very beginning, R&D has no data, but your algorithm already has a bunch of data there.
Yeah.
And how do you get those data? And it seems like the data the data quality matters a lot, right?
Yes. Like in our specific experiment, we did a 50-50 mix from expert policy and random policy.
For Montezuma.
Yes.
Okay.
Yeah. And this is also a quick comparison with like imitation learning and offline RL. And for obvious reasons, behavior cloning does not work. And I think for offline, deep offline RL algorithm, like dealing with large state space and like sparse reward, like implementing the right pessimism in practice is also challenging. Thus, the curve is at the bottom. I think like people are making progress on offline RL with image state, but that's another thread, I guess. That's the experiment part. And we can quickly summarize that in this work, we introduced our algorithm HighQ, which deal with this hybrid RL setting where you have combination of offline and online RL. And in this work, we still need to incorporate some structure to make everything works. But like this, like as I said, I hope like another wish that I have is like after this talk, you will know more about just the hybrid RL setting itself. And there are a lot of benefit of it, like compare with online RL and offline RL, as we already discussed. And there are a lot of, at least to me, future directions that are interesting. It's like first, as we keep mentioning, like HighQ can only compare with the best policy covered by the offline data. And if you want to compare with the global optimum policy, people already discovered how to solve it in tabular MDP and linear MDP. But how do we do it beyond the linear MDP? We still don't know. And again, like HighQ requires Bellman completeness assumption. And in a recent work from Ife and Irish, we have this like actor-critic style hybrid RL algorithm that has this best of both world flavor, that you only require either Bellman completeness or just standard online policy gradient assumptions. And the third question is like, as we show, like this work, we combine hybrid RL and structural assumption, but are the structural assumptions necessary? We still don't know. And there's many more interesting questions, and I'm happy to discuss after the talk. And that's it. That wraps up my talk. And thank you everyone for coming, and all the great questions. Thank you.
Thanks a lot, Yuda. I guess I'll leave the question to the audience. And first, I think Ethan already asked a question. Are there any finite sample analysis for offline and online data? Any trade-off between sample complexity of offline and online? I think that's a good question.
Yeah, in this work, we just naively assume like every time you do like 50-50 between online and offline. So the sample analysis is like whatever number of samples online you need the same amount for offline. We didn't do any like more fine-grained analysis on how do you actually do it like more optimally.
I see. So, but if you want to split it, then intuitively you should think like offline scale with the coverageability and online scale with the bilinear dimension, or you actually both parts need to scale with both component.
I think it's like as we see in the, I guess in the proof sketch, like there are actually two parts, and yes, one part you need the bilinear rank, and one part you have the coverability. But we just take the max, I guess, not max, but like put everything together in the final bound.
But I think your final bound is multiplicative instead of additive, right? So
yeah. So like by putting together, I mean a multiplicative way.
Okay. I also want to summarize a bit about your result. It seems like I think I would compare your results versus like purely offline, which is like pessimism, and purely online, which is doing optimism.
Yeah.
And it seems like the true benefit is for your work is like by doing both offline and online, you don't need to do any optimism or pessimism or optimism. So which give you the computational efficiency, which is a kind of like Oracle efficiency, which is like a true shining point for this paper. But compared to the offline setting, your algorithm, because you don't do pessimism, you actually require online data. If you don't have online data, your algorithm don't have any guarantee.
Yeah.
And compared to the online algorithm, you can only compare to the best policy covered by your offline data. You cannot compare to the true policy, true optimal.
Yes.
Well, for the online, given the number of samples, you can already compare to the true optimal.
Yeah. Thank you. I think it's a great summary. I think that's like, I guess like a drawback at like at least the current algorithm itself. But I hope like there will be more advances, at least in the setting itself. Like we still don't know if that is real for the hybrid setting itself.
Sounds good. And there are also some questions. First one from Jun Tao. Feel free to speak out.
So I just had a question on the results that you showed with that graph. I believe it's like 50% expert and 50% like suboptimal or unlabeled.
Yeah, yeah.
Or from a random policy.
Yeah.
So I'm wondering how convergence does with a completely random policy. The rationale being like perhaps the random policy provides better quote unquote coverage than the expert policy, but not necessarily like the most optimal actions in each state.
Yeah, yes, I think that's a great question. Like, as I said before, like the coverage is not explicit, meaning that you don't need expert policy to actually collect your offline data for you, as long as your offline data set covers it. But like, at least from the Montezuma revenge benchmark, I don't think if you use a completely random policy, it will actually cover the trajectory of optimal policy. But like, I'll say like in the theory perspective, if you just run a random policy and you have a non-infinite coverage terms, then it should work.
And would it like, is there any comparison between it working better than like a 50-50 split between expert and random policy, or is there no?
Yeah, we didn't do at least do that like pure random, at least in this experiment, because it's not gonna cover the expert policy at all. Like, I suspect it won't cover any good policy at all. So
I see.
Yeah.
I see. Yeah. Thank you.
That's good. I think Chava is next.
Yeah, I can follow up to that. So maybe I have two questions. So one is for this. So if you, like, what's your guess? If you reduce the amount of data collected from the random policy, how would it impact the results? Like, how important was it to actually include the random policy in the offline data collection phase? That's question number one. And the other is follow up to Chi's question, which is kind of like trying to go after like the pros and the cons of this idea. And so there, I think that one more thing could be good to discuss. What is the best case scenario of this method in terms of like comparing both to the alternatives, right? Like what would be that? Like when does this shine? Like what is the recommendation when to try this?
Yeah. For the first question, I'm just trying to see if I understand it correctly. You're saying like if I vary, say like the amount of random portion in your offline data set, how does it perform in practice? And it's in this curve, and you see it's actually like it does not matter that much. Like this green, wait, what color is it? Dark blue, orange, and green curve are like HighQ using different quality of offline data. Like it's like 100% expert data, 80% expert data, and 50% expert data, respectively. And you see, like the curve are basically the same. I haven't tried like even
50
more.
is like the hard case, and 100% of the expert is like easy case.
Yes. But like I haven't tried, say, what if you do like 99% of random policy and 1% of expert policy?
Sure.
Yeah.
I would expect that. Like that's crazily bad.
Yeah.
Sure. No, yeah. So this completely answers my question in a way. Yeah. So it seems to suggest that at least in this case, the algorithm is really great in filtering out kind of irrelevant signal from the training data, which is this random policy is going to irrelevant places. It doesn't suggest that it can somehow take advantage of this random data in any ways, like the stitching way or whatnot. It probably can't in this case because it's like this random data is just maybe completely irrelevant and the expert is already. But so this kind of raises the question. I guess you alluded to that behavior cloning would do terribly if you have the mixed like the 50% random data, and but if you had 100% expert data, would behavior cloning be kind of similar to what we see here?
Yes, I tried. Like, if you have 100% expert data, behavior cloning could be on average like 4K or 5K around that. I think there are still some like compounding.
It's not doing better. It's somehow it still needs this verification that the online data is right. Like, yeah, I assume that what happens is that behavior cloning introduces some errors which never get corrected, and they are pretty detrimental. Yeah. And if you're running this online component, that it introduces the error, and then it's like, oh no, like that's not good.
Yeah.
Okay. So you're saying there's some robustness issue about the imitation learning. If it goes to somewhere you have never seen in the data set, then it's screwed.
Yes. And I guess to Chava's second question, where does it shine? Let's say compare with like, compare with like pure offline RL. I guess one thing is like in the corollary we said, if the offline data set covers the expert policy, say like if you have like pi star coverage, we know that in pure offline RL, you need more assumption, right? Like pure only pi star coverage is not enough.
Very good point.
Yeah, and but like it will work really great in our setting, but like the argument is also counter argument is also like we are also using like extra information or assumption. So, but like I think like a pi star coverage is a nice setting, and there is a hybrid RL setting.
So when does it really shine? Like, what's the ideal case? If you need to summarize it, what's the ideal case for the algorithm for as compared to, let's say, simple alternatives?
Like I guess like as I just.
Well, what is simple alternatives you're talking about?
I guess behavior cloning would be one. I guess we just discussed that, and the other is. I guess what people run, maybe epsilon greedy for the online case, because that's what people run, not any optimistic algorithm.
Yeah, I think as we just discussed, if you have like pi star coverage, and by that I mean like not purely expert data, right? Just pi star is covered, then I think it's a very ideal setting for hybrid RL, because like for offline RL, you do need this like extra assumption, right? For offline RL to work.
I guess also the other thing is like when the exploration is difficult, so epsilon greedy or like R&D would not work very well, and then you cannot run this very complicated optimism algorithm because computational constraint, and then this algorithm will be very good.
Yeah, that's maybe the other side.
Mm-hmm. Yeah, by the way, regarding to imitation learning, Ethan was also saying the previous thing he mentioned about adversarial imitation learning also take advantage of online interactions. So it sounds like quite related to about the robustness we're talking about.
Yeah, thank you for the pointer.
Oh, Ethan, you have another question, or?
Yeah, I just have some final remark. It's like, I think the advantage of using reinforcement learning with reward is that if we are using purely imitation learning without any information regarding the state, we just cannot kick out those bad trajectories in the offline data. That's the case. And that's it. It's like with more information, it's like adversarial imitation learning, you only gather more states and you do some moment matching. So there are some blindness in it. But definitely if you try like 80% expert and 20% nuance naive policy and you run some adversarial imitation learning, possibly gonna work.
That sounds good. And I guess we are kind of like also way over the time. I guess if no other questions, I think that will be the end of the talk today. Yeah, let's thank Yuda again about this.
Thank you, everyone. Yeah, but just the final remark is like this slide.
okay. Yeah.
Sorry, everyone. Like I tried to cover this, but like I guess we don't have time. So like if anyone's interested, this is like okay, one sentence summary. It's like hybrid RL versus analogy of like dagger versus behavior cloning. In our analogy, it's like hybrid RL versus pure offline RL. But if you're interested, you can check out this slide.
Okay, I will switch off recording now and we can carry on with the discussion after that.
Sounds good.